Hello, everyone. Right, so the concept that we are going to explore today is called normalization. Okay, so this is a really interesting concept and a really important one when it comes to a lot of machine learning algorithm. Right, it's a common pre-processing step that we do before we feed our data into a machine learning algorithm. Right. So before I explain what exactly is normalization and what it does, what kind of problem it solves and everything, let's try to look at, at a sample data over here, right? And try to understand what sort of a problem would this data set give us. So imagine the situation that is, I'm using two features, age and income, right? In order to predict if a customer is going to purchase my product or not. Obviously, in a real case scenario, your purchase decision of the customer is going to depend on a lot of other features, right? But for the sake of simplicity, right now, let's just have a look at these two features. That is age and income. Okay. So something that I can observe right away just looking at this particular data set. Okay. Let's first try to compare the range of these two features, that is age and income. Range is basically what? That is my maximum value minus my minimum value in a feature, right? That is to say, over here in age, my minimum age is about 25 and it is going all the way till 50. So this is the range of features, a range of values that my feature age is taking up, okay? And this is for age. And when it comes to income, right? So I'm starting with somewhere around 30,000 and going all the way up until 150,000, right? So my age in this case is about 25, that is 50 minus 25. And in this case, it is about 120,000. So this is my first observation. That is the range that each of these features are operating on is very different, right? So the range the income is operating on is much higher than the range your age is being recorded. That's my first observation. Keep that in mind. Now let's see how this could pose a problem when it comes to your machine learning algorithms. Okay. Let me clear out these calculations. I'll do that in real time so that you guys can understand the problem. So over here, I'm going to make a small assumption that you know about the machine learning algorithm that is KNN. Even if you do not, that's okay. I'll tell you the essentials that you need to know in order to understand the concept of normalization. Okay. So imagine I have a data set like this. On the x-axis, I'm plotting the ages, and on the y-axis, I'm plotting all the incomes. Okay. And I have a lot of data points around here. Consider each of them to be different persons or different person of interests, right? And these red crosses are the ones who did not make the purchase, right? That is the 0 over here. And the green ones are the one who made the purchase. Okay. So if I get a new data point, right, this is my existing historical data. If I get a new customer in my customer database, right, and he lies somewhere around here, that let's say he's about 31 years old, let's say, and he's earning somewhere around 80,000 rupees, okay, or $80,000 or whatever. Okay. So if I want to predict if this person is going to make the purchase of my product or not, I can do that by analyzing the neighbors of this particular point, right? I can say, let's say I can take the 5 nearest neighbors of this particular point. That is, it could be this point, this point. Okay, let me mark these 5 points over here, right? And I can take a vote as to what this particular new person is going to do, right? In this case, since it is the case that 3 of the neighbors of this particular data point are going ahead with the purchase, it is very likely that even this person is going to make that purchase. Okay. But the thing is, in order to calculate which are the, or in order to figure out which are the customers who are its closest neighbors, I have to calculate the Euclidean distance between this point and the rest of the points, right? Euclidean distance is one of the way to do it. There are other methods as well. I'm not going to deep dive into that yet, but Euclidean distance is one of the ways that you can estimate the distance between these points, right? Like this. So the formula, if you want to estimate the distance between 2 points is, let's say y2, I'm sorry, let's say if you have 2 points, that is x1 and y1, and you have a x2 and y2, right? So distance between these 2 points is given by the formula, that is root of x2 minus x1 the whole square plus y2 minus y1 the whole square, right? So this is the Euclidean formula which is going to help you arrive at the distance between the points. Okay. Now we are approaching what actually the problem is, okay, and it is going to become much more clear to you. Let's say if I want to calculate the distance between our new point over here and this point, let's say, right? So let's try to approximate what the values are going to be. Let me say that this white point over here is, the age is about 31, okay, and the salary is about, let's say, 80,000, okay. And the other point, that is this green point over here, let's say the age is 35, okay, and the salary is again a bit 80,000 kind of a point. Let's say, for the sake of demonstration, let me modify that point. Otherwise the difference is not going to be very evident to you. Let me push that point to somewhere here. Okay. So now this person is earning up until, let's say, 90,000. So I have someone who is 35 years old and is earning 90,000 rupees. Okay. So these are my data points. If I want to calculate the distance between these two, what is my formula going to look like? Just substituting the points over here, I will get to see that it is 35 minus 31 the whole square plus 90,000 minus 80,000 the whole square. All right. That is to say, when I simplify it again, I would get something like 4 square plus about 10,000 square. So the problem is quite evident right now. Let me elaborate upon that. So the portion that your age is contributing towards the distance or towards the distance calculation is very less compared to, or it's relatively negligible compared to what your income is contributing towards the distance. Your age is contributing about 4 square, that is 16 units, and on the other hand, your your income is contributing a good 10,000 squares, right? So what happens is, when you are calculating the distance between the points over here like this, right, your age is not going to have a lot of say. On the other hand, even a relatively low difference between the income 80,000 and 90,000 in terms of income are not really that much apart, right? But still it's going to contribute a large portion to the distance calculation, right? That is to say, even if your age was really wide apart, let's say if you were even looking at ages that were somewhere, let's say, a 50 and a 25. Even in this case, right, your age might end up contributing about 25 square when it's over here. Let me make that clean. right? It's going to contribute 25 squares over here, but still it's negligible compared to what your 10,000 square is contributing. So you see the problem over here, right? Your income variable is overshadowing, it's overpowering the contribution of the age variable. But we do know that, right? We do know that age is an important variable, right? What age you are as a customer has a lot of say whether or not you're going to buy that product, right? So it's an important feature, but it is getting overshadowed only because of the scale that it is being recorded in, right? So this is the problem that we face when we are working with features which are in very different scales. So what is normalization? So normalization is a process that is going to help us to bring all these values into comparable range so that none of those features are going to, you know, overly contribute to the predictions or something just because of their high values. Okay. So let's have a look at how normalization work. Okay. You have multiple methods that are attributed to normalization. There are multiple ways that you can carry out this normalization. And one of them that I'm going to discuss over here is called min-max scalar, right? So this is the one that I'll be discussing in the video. We'll be carrying on with the other normalizing methods and other videos. Okay. So wait for that. But for the time being, let's have a look at what min-max scalar is and how it works, right? So your min-max scalar is going to basically scale down your whole feature, right, in the range of 0 to 1, right? So how it does that? Let's have a look. This is the formula associated with min-max scaling. It says that your normalized value or your scaled value is going to be the age. Let's say I'm looking at age, for example, right? So the age that you are normalizing, you are scaling minus the minimum age divided by the range, that is the maximum age minus minimum age, right? So our minimum age in this particular case is 25. The maximum age is 50, right? So your value that is 25 over here would be scaled like this. It would be basically 25 minus 25 over 50 minus 25, right? So that is to say it is going to become 0, which is why I said that all your values in this particular age column are going to be scaled to values between 0 and 1, right? So obviously the minimum value in the feature, that is 25, is going to become 0, right? That is going to be the case in every feature when you are carrying out min-max scaling. So let's have a look at 45 over here. That will be something like 45 minus 25, right, divided by, again, 50 minus 25, that is 25. So this is going to be what? 20 over 25, right? So that is something like that is, sorry, that is 4 over 9, right? That is the value, which is basically 0.8. So similarly, I've calculated the scaled value of your all of your ages, and you would see just the way that 25 was getting scaled to 0, the maximum value in your age feature, that is 50, is going to get scaled to 1, right? And everything else is going to be in between. So this is how min-max scaling works, right? So you're basically bringing all of your values to a range of 0 to 1. Now you would have questions over here. If I'm doing that to age and income both, would not that, distort the relationship between these two variables or something, right? So let's have a look at that. Okay. So I've done the job of plotting the relationship between the age and income. So this is the original case when the things are not normalized. Yeah, you're looking at the original scale over here. This is what the relationship looks like right now, right? And when you scale it over here, right? So these are the normalized age values and these are the normalized income values, right? So you would say that this 0.17, 0.42, 0.75, these are the corresponding scaled values to 120,000, 80,000, 50,000, and so on, right? So you would say, just a moment, let me zoom it out. Yeah. You would be able to see that the relationship between the features over here is preserved well, right? The same way the age is getting scaled down, your income is getting scaled down the same way, right? So the relationship between the features over here is going to stay still intact. And now the advantage over here is when you're calculating the distance between the points, let's say if a new point comes up here, okay? Let's say it shows up over here. And if I'm calculating the distance between those points, none of these features are going to, contribute more than they should, right? Just because they have higher scale, like our income was doing previously, right? So that is why we have to normalize it. So understand that this normalization is an essential part, especially when it comes to machine learning algorithms that are relying on some sort of a distance measure. An example is obviously KNN, right? And then you have support vector machines as well. Even your linear regression and logistic regression, although they do not directly rely on distance measure, but if you know about the concept of gradient descent, right? So there is a concept which basically where your algorithm is trying to arrive at the global minimum, right? So this particular process can be fastened up if you are normalizing your values, right? This process of converging at the minimum is going to be sped up if you are normalizing your features. So there are advantages in those aspect as well. On the other hand, you have algorithms such as decision trees and random forest, right? These kind of algorithms which do not really rely on any distance measure as such, right? So over here, normalizing would not be of much of use maybe, right? Because your algorithm by its definition is not relying on the scale of the data. Okay. So that is the concept of machine learning. I mean, I'm sorry. That is the concept of normalization. I hope this helped you to gain some insight into it. So more of the videos and more of the concepts are going to come up. So stay tuned. Thank you.